So good afternoon to everybody. So thanks to earlier speaker that who already set the tune about the asteroids. So I will mostly talk about the meteorites and why it is important and what message it convey to us as per scientific object to better understand the solar system. So you have already got a flavor of this figure. A lot of earlier speakers, I hope they have shown it. So we will be mostly focusing with this asteroid belt, which is in between Mars and Jupiter. So these, these four planets are the rocky planets. So we call it terrestrial planets, and these four are the gas giants or the outer planets. So we will be focusing mostly on the asteroid belt. So I just put my talk in the following outline that we'll talk about the meteorite. So these are the free space material and how the meteoritics or meteorite science has been developed over time. A little bit of history. I will try to explain that how it has been developed. Meteorites, how you identify it by hand specimen or by microscopy. Then the identification, classification, and the geological context, I will touch upon a bit. And finally, I will be discussing about the missions, planetary missions on the asteroids. So what are the past and ongoing and the future missions? So meteorites basically represent, you can say it's a piece of or chunk of a rocks. It mostly made up of silicate. Silicate is mostly silica and oxygen form in a tetrahedron, and there are some iron nickel alloy. So these are the combination. So either it will be fully made up of iron nickel alloy, or maybe combination of silicate and iron nickel alloy, or mostly silicate. So these three alternatives is possible. So I'll be discussing more in the later slides in the classification. So most of the earlier concept is that meteorite is gifts from the heaven. But most importantly, is it's a natural phenomena. So we can't call meteorite which is not a natural phenomena like space junks, maybe remnant of rockets on satellites. So those are not meteorites. So because those has been not fall naturally. So the weight of the meteorite could be, it's very less, it's very lighter, 1 ounce or maybe several tons, because if it is made up of iron nickel alloy, so the weight, it will be very heavy. So it is the most abundant astro material because we don't have much about the comet sample. So if we need to collect the comet sample, we need missions. But these are the samples actually where you can feel or you can touch the material. And it is also called the poor man's space probe because planetary missions, you know that it's a lot of expenses is involved, but meteorites can come from any part of the any celestial object. So we don't tend to require any missions. It can, you can get the samples totally free of cost. So these are a few known facts. It has been already discussed by earlier speakers, so I will not discuss on that. So only thing is that a meteorite, there is a two kind of phenomena. One is the meteorite fall, means there are some eyewitness because somebody has to see that something is falling from the sky. So that we call it a meteorite fall. And meteorite find means we don't know actually when it fell. So later on, we arrange for field trip or field expeditions to collect samples. And if you lucky enough, we can get the samples. And this is called that meteorite find because we don't know the exact date of fall. Another important part is name. So how to name the meteorite? So if there is a fall, means we try to get the name of the village, town, or maybe the nearest subdivision, maybe sometime district. For example, there is a fall in Katol village, so we call it a Katol meteorite. But the problem arises when there is a find, because we have a expedition to Antarctica and some hot deserts, but there you will not expect any landmark. So there is a problem. So how to name it? So this is one of the examples that ALH 84001. So it means that there is an expedition in 1984. That's why the 84 number has come. And ALH for Allen Hills. So there is a hill in Antarctica called it Allen Hills. And this is the first sample we got. So this is how it named. So we when there is an expedition, so we have to careful about the when the expedition, year of expedition, and the nearest means landmark, means it can be there is inhabited area, so there should be some hill we can name as per the hills and the number of sample we got. So this is how it, what is the convention. So this is the schematic representation actually. So meteor is, it doesn't represent any object, means it is just a streak of light you can see in the atmosphere. So the object is got burned due to atmospheric drag, but the problem arises when the mass of the object is relatively heavier. So sometimes they reach almost near to the surface, and if the mass is very heavy, they can impact on the ground and you can get some impact crater. For example, in India, you might have heard about the Lonar crater, Ramgarh crater. So these are all crater has been developed due to the impact of the asteroid. And you have to remember that when the mass is heavy enough, which can overcome the drag of atmospheric drag of Earth atmosphere and can reach the surface and can, due to high impact, it can produce a sometimes crater, sometimes little scar, or depends. Everything depends on the mass of the objects. So this is one of the example of the meteor shower. Sometime, if you remember the earlier figure, that sometime fragmentation happen in the different atmospheric boundaries. So you know the troposphere, stratosphere. So this kind of fragmentation can happen. So instead of single stone, we can expect large number of stone of different masses. So this we call it a meteor shower. The interesting part is that if you want to look for the heavier mass, you have to traverse along the trail direction. So this is the trail direction. So shower came from eastern side to the western side, and we can get mass distribution of meteor shower like this. So this is look almost as ellipsoidal distribution. So if you want to search more meteorites, we need to travel from this western side to the eastern side. So how the history of meteorites? So as I already told that earlier, the belief that it's a nature of gifts, nature, but it's a gift from the gods, and it also involves some supernatural powers. So even in the Mecca, the black stone in Kaaba, that also believe that this could be a meteorite. But anyway, later on, a scientist has investigated that this is not a meteorite. And this is some interesting story also developed based on the meteorites. So some of the very enthusiastic poet like Sebastian Brandt, so they try to figure out, okay, they try to sketch the meteorite with, they added some horn-like features, and they put the color of the cloud also dark. So this could be a sign of omen, actually means something is happening. So actually try to encourage the king that, okay, your enemy is coming from that side of a certain directions, so you have to be careful. So this kind of story can develop based on the meteorite. So he can add some more punchline here. So some of the uh, dead birds fall from the sky. Some of the animals, they hide in the burrows. So these are the sign of omens, means something is happening. So you have to be careful. But scientists, they always look for the what is the reality. So this man Chladni, he is known from for the father of meteoritics. So he wrote a book that, and he also mentioned that he has witnessed some fireball. So something has coming from the sky. So it is not a terrestrial object. So something is happening. So we can expect some outer space materials. But he deserved a lot of resistance from common people. Not only the common people, even the scientific community also put a lot of resistance. That okay, what you are telling, this is not correct. So we are still not a belief that there is something can possible to come from the outer sky. But later on, there is another incident of the shower, means a meteor shower. So we can expect a lot of rock fragments. So this old cottage is another example of the meteor shower. And Edward Howard, he is actually a British chemist. So he found several grain which is rich in nickel and iron. So this is not very similar to what we expect in the terrestrial, means in the earth rock. So he mentioned that okay, this could be something different which is unusual. So we need to investigate further. And finally, this is the man actually is a physicist. So he tried to map on meteor shower. So in 1803, so there is a meteor shower where they have tried to collect almost 3,000 stone. And this is the map of the shower actually, he mentioned in his manuscript. And then the French minister, okay, they try to believe that, okay, there is something. So Academy of Sciences also started to believe that, okay, something is possible to come from the outer sky. So you need to investigate further. You need to examine what is coming from the outer sky. So this is how the meteoritics, means meteorite science, gets some credibility. So and evolve further. So this is some of the example that how lethal could be a meteorite. So this is one of the event in Siberia, Tunguska. This is in 1908. So there are several trees. They fallen. They're lying like this way. Means, but there is. They didn't find any meteorite or any stone from the outer space. But this is little bit unusual. So later on, then there is a revisit was there, and now we get to confirm that okay, there are some airburst explosion took place, but there is no meteorite, means rock fragments survived this incident. So this is the main cause where the all trees got burned. Sometimes it can damage the property, like you can see that one car has been damaged. And this is one of the event, a recent event actually. This is in Chelyabinsk. So scientists, they have identified several fragments through telescope, but they found only one segment, one fragment. So this is how the other examples are. It can make a hole in the roof. And this is one of the example from India. So it can produce a this kind of indent on the floor. But can meteorite a human killer? So there is no example, but there is an publication is there. And but the in the as per the manuscript, so there are one incident where the meteorite killed a man and other man got paralyzed. But this has been happened in long ago, because it's in 1888. After that, there is no such example that meteorite can kill any human being or any other animal. But okay, there is example of devastation, means we try to link actually. So you all know about the dinosaur got extinct around 65 million year ago. And in the similar age, we got some kind of clay minerals where the iridium concentration, so iridium is kind of a noble element. So if we get a higher concentration of iridium, so this is something looks unusual, but it can be very common in the earth rock. So, but iridium is very high in the meteorites, so extraterrestrial objects. So then we try to believe that okay, there may be some kind of one impact took place during the time 65 million year, which may cause this dinosaur extinction. So we have a geochemical evidences and we have some fossil evidences. Then we try to connect the both the incident together, but there is still some dispute over the exact chronology. But still, if we assume that okay, 65 million year is the date, then we can correlate these two incidents. So this is the actually crater I was talking that this is a Chicxulub crater, and this is actually in the offshore of Mexico. So this is not in impact on land. It is on sea floor, means coastal area. You can say subsea floor area. So total diameter is around 190 to 200 kilometers. So it's a huge, and this huge meteorite or asteroid impact can capable of uh, global extinction. So, so this is one of the theory. Still, we are believing that okay, the Cretaceous mass extinction is mostly due to the meteorite on giant meteorite impact. So, next couple of slide, I will try to uh, explain why we study meteorite and how to identify how old they are, how long they are in the space, and what are the classifications. So meteorites is very important because meteorites contain some star objects, means some stardust. They contain some pre-solar object also, means some objects are believed to be formed before the early solar system. So they sometimes occur as an inclusions. We can talk about the Earth Moon system based on the lunar meteorites. Meteorite can also cause volcanism, mass extinction, what I already explained that, and there are also some atmospheric changes took place. It can also impact, it can cause earthquake, maybe local scale or tsunami as well. And sometimes meteorites can cause the hydrothermal mineral deposit, like in Sudbury, Canada. The nickel copper deposit is formed due to the Sudbury impact crater, where the impact actually remobilize the elements, means the hydrothermal, means the element nickel and copper, remobilize it and they reprecipitate it in the form of hydrothermal minerals. So there is still a hypothesis that the Earth life has been emerged due to the cometary or asteroidal impact, but still this is in hypothesis stage. There is no solid proof yet. So how the asteroid belt actually this has been concept has been developed. So this is some of the prediction that TTS and Bode they have did that this is the equation they try to follow that, and they found an interesting thing that there is a missing of a planet between the Mars and Jupiter. So this is the actual distance measured by telescope, and this is the calculation. So this is the story actually. So how the invention of this asteroid belt comes from. So there is something is there, not in the form of planet, in the form of asteroid belt. So this is how the concept of asteroid belt comes in the picture. So how old is the meteorite? So we all know the age of the solar system is around 4.5 billion years. So some of the early from solid part object like calcium aluminum rich inclusions, so they are also very old, sometimes equivalent to our solar system. And these are the primitive chondrite, they formed very early, but lunar meteorite and Martian meteorite is it's can be older as well as the younger, because it depends on, because if the uh, volcanism occurred later or recent times, you can always expect some younger rocks. And these are the actually short-lived radionuclide we generally use to date the object like calcium aluminum rich inclusions or the chondrite to constrain the age. Another important part is the cosmic ray exposure age. Actually, this can tell us about how long the meteoroid remain in the space. So what happened when the meteoroid they roam around in the space? So there is a production of cosmic rays, but the production of cosmic rays stop when they enter into the Earth atmosphere. So we have to measure the cosmogenic radionuclide here. And if we measure the cosmogenic radionuclide by mass spectrometer, we can infer that how long the object was remained in the space. So this helps us to infer the cosmogenic radionuclide age, or the cosmic ray exposure age of the meteorite, and we can get some estimation. Okay, so here is the plot actually. So we can see that this is a H type of chondrite. So majority of the samples or meteorites, they are giving or yield a cosmic ray exposure around 6 million years. So this is the distribution. We can say that okay, most of the H chondrite, they are remain in the space around 6 million years before into the Earth atmosphere. So there are several actually radionuclide isotopes. So I'm not going into the much detail due to time constraint, but this is the basic idea how we calculate. So morphology, so as you know, the meteorite, this is a solid object. It's coming through the Earth atmosphere. So the outer area, outer portion should get burnt, and you get this kind of fusion crust, and you will also get thumb-like impressions. So we call it a regmaglyph. It can be simple, it can be compound. And another interesting part is the flow lines. So it actually help us to identify which one is the frontal side and which one is the rear side. So flow lines is like this, means it travels like this. So this is the frontal side and this is the rear side. There can be some micro fissure developed due to the uh, physical condition in that high heating condition during the atmospheric entry. And this is some more example. So this is one of the meteorite. This is from Martian meteorite. You can see radiating flow lines, beautiful radiating flow lines. So this is the frontal side, and this should be the rear side. So we can also infer the different generation of fusion crust. So which one is the younger, which one is the older. So this is the basic classification. We already discussed that some are stony meteorite, which is mostly composed of silicate minerals. So we will get this kind of silicate droplets. We call it a chondrules. There are several classification of chondrules. So I'm not going into that details. This is the actually combination of silicate and the iron nickel alloy. So the host here is actually iron nickel alloy, and the guest, you can see these are the silicate mineral. It is olivine or pyroxenes. And the another type is the fully made up of iron nickel alloy. So this is the iron meteorite. So you can see the beautiful texture of Widmanstatten texture. So basically this is the intergrowth of two mineral. We call it a kamacite and tannite, and they form in a particular crystallographic direction, and the resultant, you can see the beautiful texture. So this is the basic idea about the classification. There are many complicated classification, but I'm not going into that details. But we generally our the false statistics claim that mostly we are expect the ordinary chondrites, iron meteorite and stony meteorites are very less. So these are some other classification. We call it undifferentiated and differentiated. Undifferentiated means you can expect a homogeneous body. There is no layering. But differentiation means due to heating, the heavier elements they concentrated into the core. So we will get the iron nickel alloy at the core, and gradually upwards means you will get the lighter element and the lighter mineral also, because mantle is little lighter as compared to core, but little heavier as compared to the crust. So this is the distribution. So there are many more classification like ordinary chondrite. There are H, L, and LL type based on the metal content. There are carbonaceous chondrite which are supposed to be very primitive, and there are different clan also, carbonaceous, Ci, Cm, Cv, and there are astatite chondrites. So these are the classifications. So different authors, they try to classify in different way, but the bottom line is almost similar. So uh, these are the structure of chondrites. So I already told you can expect silicate droplets. They are a different kind of olivine and pyroxene mineral. Some kind they are radial pyroxenes. Some it is a porphyritic olivine and pyroxenes. And these are the matrix and these are the chondrules. So there are another petrologic type. So some of the meteorites you can expect some aqueous alteration, because meteorites, during the accretion they can accrete rock and ice. So due to the accretionary heat, the ice can melt, and when the water is available, water can interact with the anhydrous mineral and produce secondary minerals. So this is the fundamental aspect for the meteorites which undergoes aqueous alteration. But there are some anhydrous meteorite which doesn't contain ice, but there are some short-lived radionuclide like 26 aluminum and 60 iron, which can produce heat and which can metamorphose the mineral. So this causes the thermal metamorphism. So this is the different type, actually 4, 5, and 6, and this is the aqueous alteration 1, 2, and 3. So 1 is very highly altered, and 2 is means moderately altered, like that. But the thermal metamorphism, it goes this way, means 6 is very highly metamorphosed. So these are the general description you can get in any textbook of meteorites. These are, I'm just skipping it because this is the further classification. So this is the basic representation of the meteorites. So if you have a sample like this, which is mostly made of silicate, so you can expect, okay, this can come from the outer skin of a differentiated body. If it is a differentiated meteorite, so it might have blasted from the crust of the differentiated body. It can come from the mantle as well, but if it is an iron meteorite, iron nickel alloy, so it has to come from the core area, inner core area. But if there is a combination of both, like we call it a palisade, this is one of the most beautiful meteorite available on Earth. So this must have come from the interface between the mantle and core, because you are getting the mantle silicate mineral here as well as the core metals. But there are discrepancy and disparity is still there. Some people believe that, okay, this can be formed due to ferrovolcanism, but these are all hypotheses. Some more study is required to get a conclusive view. So this is the iron meteorite classification. So we will get this kind of structures after etching. Etching means you have to treat with ethanol and nitric acid. And some of the iron meteorite are structureless. There is no structures. These are the chemical classification. I can skip because these are a little bit complicated. I can skip it. So I will go to the missions now. So why we need a mission to asteroid? The main problem is that meteorite sample, okay, we have the sample, we can study them in the laboratory, but the problem is we don't know from where the sample come from. We know it has come from the asteroid belt, or it may come from the moon. We call it a lunar meteorite, though it is a misnomer, but we call it a lunar meteorite. Or sample from Mars, we call it a Martian meteorite. But in the asteroid belt, there are lakhs of means asteroid where we don't have any idea from which parent body the meteorite has come from. So we need to study the asteroid, means we need to see the what is the kind of parent body there, and also we need to study the active space environment, means the space weathering effect. There is a continuous bombardment of meteorites, so we need to study them, and we need to study the astrobiology in the active environment. So because this is only possible when we have a in situ measurement in any planetary mission to asteroid. And also finally we need to develop our planetary defense system, because there is a possibility that asteroid can uh, means come towards the earth orbit, and there could be a future collision with the earth. But we have to think of though it can't be a reality now, but we need to think for the future. And also we can develop the in situ resource utilization, means some of the meteorites, they are very rich in the metals, sometimes it's a platinum group of elements, maybe rare earth elements. Those are critical minerals or strategic minerals. So maybe we can think of some time in the future that okay, we can, is there any possibility to mine them, or whether it is economically exploitable to bring the sample from this asteroid to the earth. We have to develop this exercise also from now. So this is one of the missions. This is actually the first missions, Hayabusa. So this actually was a mission planned to target the S-type asteroid. So this is the Itokawa asteroid. It's the stony type S-type asteroid. But the problem is the recovery of the sample is very less. So it is less than 1 gram. We have the Japanese space agency JAXA. They carried out this exploration, but they only able to extract some fine dust and fine mineral grains. So anyway, the mineral grains we studied in the laboratory, and we got that similar kind of meteorites also we have in our collections. So the main science highlights of this asteroid was okay, it's a low metal LL type chondrite, and which we have huge collections of the meteorite as well. So this could be one of the parent body, whatever LL chondrite we have in our collection. So we can say this could be one of the parent body. But this kind of asteroid, there are plenty on the asteroid belt. So we need to explore the other possibility also. So the next mission is the Hayabusa 2. So it's a different kind of asteroid. So it's a basically C type of asteroid. So carbonaceous type. Here the recovery is little higher, because you can see the mass we recovered by the JAXA. And this is the uh, sample holder image. You can see the rock fragment they have collected from this asteroid. And there are these are mostly similar with the CI type of chondrite, because there are plenty of secondary minerals also uh, examined in the this collected samples. And this parent body also dated, actually, means this rock fragment also dated, so we can claim that it has been formed just after 2 million year of the solar system. So this is one of the important discovery from an asteroid missions. And the latest one is the Bennu, the OSIRIS-REx mission. So NASA has conducted this mission. So here the recovery is very high, means more than, they claim that it is more than 30 gram. The asteroid is actually B-type asteroid. So there are many major findings actually. If you see the science issue, so you can see many papers on this Bennu asteroid. So they have found some of the this kind of white color vein. They call it a carbonate vein, and even they try to infer that okay, this vein has been formed due to the hydrothermal, late stage hydrothermal activity also. So these are the spectral match of this Bennu samples. So they find a very good match with other CI or CM, other carbonaceous chondrite samples. So these three missions are mostly on the means S-type asteroid. So, but NASA also launched these missions on the metallic asteroid. So 16 Psyche is the asteroid name. Actually, they try to carried out the experiment there. So this is the some of the information of this asteroid. Means diameter is around 200 kilometer. So it's supposed to form exclusively iron nickel alloy. So there is no silicate. There could be silicate inclusions, but majority of the will be the iron nickel alloy. So this has been actually thought to launch a few years back, but there was on hold for a year due to some technical glitch. But it has been launched last year actually, and supposed to be reached there in 2029. So we have to wait for another 5 years to get the information about this metallic asteroid. So how to identify? Because if we try to carry out on field expedition in the cold desert area, so this is an example in the Antarctica. So you have many rock samples. So these are all earth samples. So we have to find the extraterrestrial object within among these rock samples, which is really challenging. So we can adopt some of the very basic methodology. Means we can use some magnet, because due to higher iron nickel alloy, it's supposed to attract the magnet. It should be density should be a little bit higher as compared to the earth rocks, but these are very preliminary. Means this can't be conclusive. You have to remember that. Shape, I have shown that you can expect some fusion crust, but this also uh, means got weathered due to over time, years, million years, because we don't know the fall date. So you may not get the fusion crust, because you can expect fusion crust only in the fresh sample. So this is another your life will be much more difficult situation, because you don't have any fusion crust. It will be very similar to the earth rocks. Aerodynamic shape, sometime may help, but again it's some kind of bias is there. So if you have earth rocks which is aerodynamic shape, then it can be misleading also. And surface feature like flow lines, if it is a fresh, then you can able to identify. But if it is a very old sample, the flow line also means fade away. So the final verification you need to do in the laboratory. And another important information is that we know the majority, most of the part of the earth surface is in the oceans. So we are losing many meteorites in the oceans every day. So and that part we can't collect the, we can collect, but again you have to do the sea floor coring drilling. Then you have to retrieve the core, you have to search for the extraterrestrial material. So again this is a means high cost is involved, and also a lot of time is involved. So this is the another fascinating story of that how to know that whether this sample has come from the Mars? So what happened in the meteorite sample? There are some fluid inclusions in the glass in the form of glass. So when we measure the uh, atmospheric composition like noble gas, xenon, argon, neon, krypton, so we have a data from the laboratory, and we also have a data from the Viking lander which explored the Mars in the year of 1976. And we will have a very good match if the sample has really come from the Mars. So this is the way we need to validate or need to verify whether a sample has come from the Mars, whether a sample come from the moon. There are some other example also you can use with the help of mineralogy, because Earth mineralogy is different from the Mars. Earth mineralogy is different from the moon, and also different from the Forvesta. But one of the conformative story can tell the oxygen isotope, because oxygen isotope, if you see the oxygen isotope, that is also very distinct for different celestial object. Like for Earth, it is different, but Earth and Moon oxygen isotope is very similar. So that's why the hypothesis is still hold that okay, Moon has been formed from the Earth due to the collision with the Earth, Mars-sized impactor, Moon has been formed. So this entire story is based on the oxygen isotope, because Earth and Moon oxygen isotope is very similar. But if you see the other bodies, their oxygen isotope is dissimilar and distinct. So this is one of the way we can verify whether the meteorite has come from which particular body. So I will end with the future threat, but you don't need to worry about, because it may not happen. So there could be a possibility of collision of Earth with the other asteroid, but space agency already has thought about that. So they have already carried out an experiment called DART, double asteroid redirection test. So this has been carried out in 2021 and 2022. So what happened, what they did actually, so this is the original orbit of this is a binary asteroid, Didymos and Dimorphos. So they try to collide with this asteroid, and then they deflect their actual orbit, and after that collision they find a new orbit like this, the blue color. So the NASA, they successfully demonstrated this, and if there is any chance in future that okay, there is a threat on asteroid, future collision, possibility of collision is there. So they are now where they are ready to prepare that okay, they can deflect the asteroid for future possible collisions. So this is the meteorite fall and find in Indian scenario. So we have already almost more than 700 meteorites in our collections. So it cover almost majority of the states. So somehow the most of the meteorites fall and find from Rajasthan area. I don't know the exact reason why it is so, but this is the fact. And even last year also we have collected a meteorite from the state of Maharashtra. This is Kopargaon. It fell in 24 January 20 year of 2023. And there are some recent also very interesting meteorite like carbonaceous meteorite Mukundpura, uh, which has been collected from Jaipur in the year of 2017. And you can see the statistics that most of the meteorites are ordinary chondrite, means either high iron H type, low iron, low metal, low iron L type, or very low iron, low metal LL type. So this is the distribution actually statistics we have, that most of the falls are ordinary chondrites and carbonaceous chondrite is very less. So I will end up here.